Hello everybody. So today we will discuss about parallel operation of a transformer. This parallel operation of a transformer we need, let's say, in a locality where already one transformer was serving its purpose, and gradually the demand in that area has increased because the population in that area has increased. So, and let's say if I overload my transformer, so we have seen that obviously the voltage regulation of that transformer will become poor, even the efficiency will go down, right? And let's say if I replace the entire transformer with a new one with higher capacity, obviously then this process will take a lot of time as well, right? And even then what would be the use of that transformer which was already there in use? So the one solution is to connect the transformer in parallel with this existing transformer. Okay, so connecting transformer in parallel means input supply is common for both the transformers, and even the load is common to both the transformers. Okay, so that what we will discuss today. Okay, let's say even this helps us, the connection of two transformers in parallel actually helps us in increasing the reliability. Let's say one transformer goes has occurred some fault in one transformer, so obviously I may use the other transformer as well existing, right? And I may regulate the load shedding and these things to maintain the rating of the transformer. So even in faulty situation, it actually increases the reliability. Okay, and in some cases, let's say where there is a lot of variation in the load. Okay, and we know that to operate the transformer at its maximum efficiency condition, we generally operate the transformer at its maximum efficiency loading condition. Okay, so let's say but there is a lot of variation in the load. So what we can do is we can connect two transformers in parallel. Let's say the load variation is of around 40 or 50%. If both the transformers are connected, they are catering, they are at the load of, let's say, 80%. Okay, so 40% one transformer was sharing and 40% other transformer was sharing. Now during night time, let's say in a locality, the load demand has reduced now. Okay, so and it has come to 40%, and this is the general phenomena and it is observed. General phenomena in the sense that before connecting these two transformers in parallel, before employing two transformers in parallel, I have already seen, okay, there are a lot of load variations are there. My transformer generally operate at 40% from this time to this time, and at 80 or 90% from this time to this time. So then I will accordingly, what I will do is I will choose to turn off one transformer. Okay, when there is less demand. So now the entire load has shifted to one transformer. So obviously earlier if 40% they were sharing, and during night time there's only demand of 40%, right? Now the entire load, the first transformer will be loaded more, right? That would be the 80% of actual rating of that transformer. So in this way we are actually operating at maximum efficiency condition again, and that's how we are able to reduce the losses. So that's why we need to connect the transformers in parallel. So obviously these things will happen in three-phase transformers, but at your level I'm just discussing about the single-phase transformers. Okay, so parallel operation of two single-phase transformers. Okay, so there are few conditions, and what is the parallel operation means? They will have a common load and common supply. Let's say this supply is coming from the transmission line. Okay, and it is feeding one transformer. Okay, and there's another transformer. So parallel operation means the source would be same for both the transformers. Similarly, the load, they would be same. So earlier, let's say one transformer was feeding this load. Now load demand has increased. So I have connected another transformer in parallel with this existing transformer, okay, to feed this load. Now there are few conditions which we should satisfy before connecting this transformer in parallel with each other. The first and foremost condition is they should be connected with in a proper dots. Right here, the importance of dot convention will come into picture. Okay. So the first and foremost condition is the transformers should be connected properly as per the polarity. As per the polarity means proper dots. We will discuss about this. And the second condition is, but this is very important condition. Okay. The second point is they should have equal voltage ratios. Okay. Then third is, so this is also important. Condition one is very important. Condition 2 is also important. Let's say 100 volt is the supply. So 100 volt on one transformer, 100 volt on another transformer. Okay. The primary of it. And secondary, let's say turn ratio is equal. So 200 volt here and 200 volt here. So then obviously you can short these two ends, right? And we'll see how if this voltage ratio is not same, then how it will cause the circulating current. Okay. The third condition is the per unit impedance, sorry, the leakage impedance, the per unit leakage impedance of each transformer should be equal. I said per unit, right? So per unit impedance, if we calculate, if the let's say the apparent power rating of the transformer is different, okay, then obviously the leakage impedance in ohms would be inversely proportional to their respective kVAs, right? So what I'm trying to say is the per unit leakage impedance of each transformer should be equal. And the fourth condition is the ratio of equivalent leakage reactance to winding resistance should be same for all transformers. So the first condition is very important. Okay, second condition is also important. Okay, but let's say, but second, third and fourth condition, I would say it's a desirable conditions, and the first condition is very important actually. We'll see how. So before connecting the transformer in parallel, actually we should know what is the polarities of this transformer. If it is if the polarity has been marked or the dot has been marked, then we can obviously we can directly connect as per the polarities. Okay, so that means if this is the dot, I will connect this to a load here. The other transformers, if this is the positive and this is the negative here, and this is the positive and this is the negative here, because the dot has been marked, then I will connect this here, the positive to the positive terminal and negative to the negative terminal. Okay. But let's say this dot has not been marked. I don't know the polarities. So actually I don't know these polarities. And I want to connect it. So before connecting it, we have to first do the polarity test. Okay, so how we will do the polarity test? So we will assume whatever the dot of the primary is, we will just assume, okay, uh, we will first connect the primary of both the transformers to a common source, and this is what you will do in one of the experiment in your next semester on machines, the parallel operation of our two single phase transformers. Okay, so here then you have to perform the polarity test. Let's say you connect it here. So I don't know the dots. What are the dots here? And even I don't know these dots. So I don't know these dots. What are these dots at the primary as well? And I am assuming that, okay, the primary's dot is located here. I'm just assuming, this is an assumption of the dots here. Okay. And let's say what I will do is, I will connect up, I will short these two ends, and I will connect a voltmeter here. And let's say this voltage which is generated here at the secondary of it is EA, because this transformer EA, this transformer is A and this transformer is B here. So if this voltmeter, obviously there would be some induced EMF, and if this voltmeter reads twice of, and this is EB. Okay, so what I said is, it should be the dot should be connected properly, and second condition was the voltage ratio should be same. So if I'm saying that voltage ratios are same, if whatever if the voltage ratios are same, whatever voltage has come to the primary of it, same voltage will come at the secondary of it, right? So I'm saying, okay, EA would be equal to EB. Then here you will get the twice of the voltage, twice of E. If this voltmeter reads twice of it, that means my dot is here, right? So in this condition, let's say, or simply I would say, V voltmeter will read EA plus EB, right? This voltmeter will read EA plus EB, right? So if you short here, let's say this is a switch, and if you short it here, what will happen? So you are shorting the entire voltage, right, across a zero resistance. You connect this, let's say this is a switch, and you have turned it on. Okay, so you have shorted this entire voltage across a zero resistance. Obviously a very huge current will flow here, and this may even damage the windings of the transformer. Okay, so this is not the connection. If voltmeter reads EA plus EB, then you cannot actually connect it into parallel. Okay, you cannot connect the secondary here. Okay, let's say if your voltmeter reads EA minus EB, and here I said that voltage ratio should be the voltage ratio should be same, that means EA is equal to EB, then in that case this V would be equal to 0, right? And that is only possible if your dot is in this direction. Sorry, so this dot is here, then I can actually turn it on. Okay, so that is the importance of the polarity. And if I connect it now, so since this potential difference between this point and this point is 0, now you can short it, right? There's no potential difference, so there won't be any current flowing in this path, right? So your transformer, you can short it. Now you see how you will connect it to the load. So let's say your polarity has been marked now. Okay, my polarity is this. Okay, so here for proper polarity test has to be performed. to connect the transformer properly as per the marked dot. So this will ensure, so proper dot and equal voltage ratio will ensure zero circulating current. Zero circulating current. If EA is equal to EB. If EA is equal to EB, then it will ensure zero circulating current. So we'll see how do we connect it in a so parallel means obviously now here, so this load now would be connected, the positive would be connected here and negative would be connected here, and similarly the positive would be connected here. Okay, let's say your EA let's say your turn ratio is not same and EA is slightly greater than EB, then what will happen? And let's say I'm just I have neglected the magnetizing current, and I am actually incorporating the leakage impedance of this transformer therefore towards the secondary side of both the transformers. So this is ZEB, and let's say this is ZEA, and currently EA is slightly greater than EB. Okay, so what will happen? So obviously since EA is greater than EB, that means, you see here, I said EA is greater than EB, obviously depending upon, slightly greater than EB, let's say, then obviously depending upon the potential difference and the impedance here, potential difference and the impedance here, it will actually push the current in this branch, in this loop, right? Because EA is greater than EB, so EA, it will push the current in this path, right? Okay, see here. So that will actually cause the circulating current in the secondary, and you'll see that it will have the effect on the primary as well. So what I said is that it has pushed the current, circulating current IC, which would be equal to EA minus EB upon ZEA plus ZEB. Let's see, let's try to first see the direction of the current, circulating current. So EA is greater than EB, so obviously it will push the current in this direction, and let's say that current is IC here, and this current will take this path, sorry, and let's say currently I have opened the switch for the load to make the analysis little easier. Okay, so now there is no load current, only there is a circulating current. So this current IC will take this path here, will come out, will go into this dot, will come out from here. Now obviously this path is open, so current won't take this path, rather won't take this load impedance path, rather it will take this path, come here, and will go back. right? Because there is a circulating path is available. Path for the circulating current is available. And if you write the KVL here, if you apply the KVL, let's say EA minus IC into ZEA minus IC into ZEB and then minus EB is actually 0. And if you solve it, you will actually get IC is equal to EA minus EB upon ZEA plus ZEB. And one more thing, you can see that EA minus IC ZEA is actually equal to EB plus IC ZEB. Okay, and these two things, if you see, is nothing but the voltage which is appearing here, V, and this is actually equal to V. So this circulating current in the secondary will actually force the, if you see the terminal voltage here, this terminal voltage, right? This V is nothing but this terminal voltage, and this V EB plus IC plus ZEB, that is this voltage, right? See here, so they are same. Okay, EA minus EA minus IC into ZEA is this voltage, right? And EB plus this voltage here, EB plus this voltage drop, because plus is here and minus is here, right? Current is flowing in this direction. It is, this is EB plus IC ZEB, and this is EA plus IC into ZEA. And what is this? This is nothing but this terminal voltage here only, right? See, right? So this circulating current will actually force to achieve the equal voltage at the terminal of it. And how it will affect? This circulating current will force the voltage which is higher, that voltage, the terminal voltage of that transformer to be lower. Okay, and for the transformer whose terminal whose induced voltage is lower, for that it will add up the voltage there, and that's how it will compensate. So what would be the circulating current in the primary side? So let's see, as per the dot convention, if in the secondary current is leaving the dot, then in the primary the current should enter the dot. Let's say that current is in the primary, if you'll see, so here this current is leaving this dot, right? So I have said, okay, this is the dot here. So in this dot, this current is entering. Okay, and here the current is entering into the dot. So from this dot, the current should leave. Let's see whether this actually makes the circulating path or not. So this is the path. This will take this path, come here, right? We'll take this path, we'll take this path, right? We'll take this path and go there. So if you see, it has actually completed its path. It is here in this direction, coming here in this direction, then here, and the entire path has been traced out for the primary as well. Okay, and see, even if you have not connected any load, because of the difference in the induced EMF, and that induced EMF difference would be because of the difference in the voltage ratio, and that voltage ratio, difference in the voltage ratio, has caused a difference in the induced EMF of both the transformer at the secondary of it. And once you have shorted at the secondary of it, it is forcing the circulating current in the secondary, and because of that there is a circulating current in the primary as well. Okay, primary as well. And obviously the transformer will have more losses now, no load, but still because of the change in this induced EMF in the secondary side, the there would be a circulating current, and that will cause more losses. So this is not the efficient way. So even we should have the equal turn ratio. Proper dot transformer should be connected in a proper polarity. First thing, because polarities are not checked and you connect it directly, then there are chances that you will short the huge potential with a zero resistance path, and that will cause a huge circulating current, and that transformer will get damaged. And let's say if there is difference in the voltage ratio, then there would be, as per the difference in the voltage ratio, there would be equivalent circulating current which will flow in the primary as well as in the secondary, even if you have not connected the load. Okay, so these two conditions we have discussed. Okay, now we will see how these transformers, so once you have connected this transformer properly, how this transformer actually shares the load.